Hello, my name is Daniel Clarkson. I'm a PhD student from the University of Glasgow, and here I'll show some recent work on the frequency time resolved imaging spectroscopy observations of solar radio spikes with the low frequency array. So solar radio spikes have short duration, narrowband bursts, and they're a signature of the non-thermal electrons that have been accelerated in solar flares. And they're indicative of processes that are occurring on millisecond timescales, so often used as an indication of the energy release period itself. Now here you can see some example dynamic spectra of spikes at various frequencies, as well as some previous imaging observations that have managed to localize the emission region, but were not able to individually resolve spikes in order to track their motion. So using LOFAR, we've been able to resolve in both time and frequency now over 1,000 individual spikes from this event in 2017, and this is between 30 and 70 megahertz. And you can see a C-class flare that's associated with a type 3 burst, as well as a type 2 that was caused by a CME. And then we have this main spike cluster that occurs post-CME. And zooming in, we can see many individual spikes within a very short period. And here we have a single well-resolved spike where every pixel can be used to generate a radio image such as this one. And here we fit the main lobe of the emission with an elliptical Gaussian and use the centroid position of that to track the motion of the source in the plane of sky across fixed frequencies. So as you can see, the spikes show areal expansion and centroid motion during the decay phase. And in fact, this motion that you see is actually superluminal, up to 1.5 C for this case. Now, this superluminal motion is not that of the exciter, but is caused by the scattering of the radio waves due to an anisotropic turbulent medium. And this causes the radio waves to be scattered preferentially in the direction of the guiding magnetic field. And this is consistent with the PFSS extrapolation of extended post-reconnection closed loops likely formed within the CME wake. And this superluminal motion suggests that we have strong levels of anisotropy along closed loops, and the dominance of the scattering on these observations would only act to increase the observed time profile, which means that the period of energy release could actually be shorter than often assumed from observations alone. Thank you.